Hi, Assalamualaikum. My name is Ali and I'm from group number 1. For this group presentation task, my friend, which is Fadil and Raimi, will present the answer for the question number 1.
So for the question 1A, yellow sodium light of wavelength 589 nanometer emitted by a single source pass through two narrow slits 1 millimeter apart. The interference pattern is observed on a screen 100 cm away. Distance between the two adjacent bright fringe is. So from the question, the question is one, the distance between the two adjacent bright fringe. This is represent the delta y. So when we see in the formula, delta y equal to lambda times d, the capital letter of d, over the d with small letter. So from the question, what the information that have been given is lambda equal to 5.89 multiply 10 the power of negative 7 meter, d equal 1 meter, and the small letter d equal to 1 multiply 10 the power of negative 3 meter. So we just substitute the value that given from the question, and we get the delta y is equal to 5.89 multiply 10 the power of negative 4.
Right then, I'm Faiz Raimi and I will give explanation for question 1b. In a young double slit experiment, the frequency of the coherent source of light is f, and the distance between screen and source is 1 meter. The distance between the source is d. If the screen is moved 5 meters further from the source, the fringe width will become. Yes, that's the question. And my answer is, it is given in the question that d is increasing and it will affect the fringe width or delta y. Based from the formula, delta y equals to lambda d per d. When d increase, delta y will increase because delta y is directly proportional to d. That's all from me. Thank you.
That's all from us. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Now, I, Amir Muzaffar bin Muhammad Shafawi and Muhammad Azim bin Abdul Talib, the most wanted students in USIM, will present to you question number 2. Do not forget to our lecturer, Sheriff Miss Laila. Okay, let's proceed to question number 2A. In Young's experiment, two coherent sources are 0.90 mm apart and the fringes are observed 1 meter away. If it produces the first dark fringe at a distance of 1 mm from the central fringe, the wavelength of monochromatic light used would be. So we can assume that 0.90 mm is the small letter d, and 1 meter away is the d. The question says that if it produces the first dark fringe, so when we say the first dark fringe in in-phase coherent source, we know that m is equal to 0. So when we know m is equal to 0, we can say that y0 is equal to 1 millimeter. The distance from the first dark fringe to the central bright fringe. So we just use the formula ym is equal to m plus 1 over 2 lambda d over d. Substitute the value which is 1, multiply with 10 to the power of negative 3 because we want to change the unit from millimeter to meter. It's equal to 0 plus 1 over 2 times 1 and lambda over 0.90 multiplied with 10 to the power of negative 3 because we want to change the unit from millimeter to meter. We just calculate and we get the answer. Lambda is equal to 1.8 times 10 to the power of negative 6 meter.
Question 2b. If yellow light emitted by sodium lamp in Young's double slit experiment is replaced by monochromatic blue light of the same intensity, what will happen to the side width of the fringe? So the question want to ask what will happen to the side width if we change yellow light to the monochromatic blue light. So we will compare the formula of delta y is equal to lambda d over d. Based on this formula, we can see that delta y is directly proportional with lambda. And by looking this picture, we can see that lambda y, lambda for yellow is greater than lambda for blue light. So if blue light used instead of yellow light, we can know that lambda y is greater than lambda b. Thus, when lambda decrease, the size fringe width also decrease. So that's all for me. Thank you.
That's all from us. Thank you.
Question 3a. What is the distance between the first bright fringe and the central maximum on the screen when the wavelength of the light from the source is 546 nanometer and the slit separation is 0.12 millimeter? The screen is 60 centimeter in front of the slits. So from the question, we can determine the wavelength distance between the slits and the screen and slit separation. So the wavelength, which is lambda, is 546 nanometer. We need to change it to meter. We need to times by 10 to the power of negative 9. Next, we need to change the d, which is 60 centimeter to meter, by time it's with 10 to the power of negative 2. Next, we also need to change the small d to meter because the value given is 0.12 millimeter. So we times it by 10 to the power of negative 3. Lastly, we need to determine the value of m, which is 1. The formula for this question, which is the distance between the first bright fringe and the center maximum, use the formula ym equal to m lambda d over small d. Next, we need to substitute the value into the formula and we get the answer 2.73 times 10 to the power of negative 3 meter.
Question 3b. In the double slit interference experiment, suppose the slits are separated by d equal to 1 cm and viewing screen is located at a distance L equal to 1.2 meter from the slit. Let the incident light be monochromatic with a wavelength lambda equal to 500 nanometer. The question is, what is the distance between the third order bright fringe and central line? And so m equal to 3, lambda 500 nanometer, we convert into 500 times 10 the power of negative 9 meter. D is 1 cm, then we convert into meter, 0.01 meter, then the D is 1.2 meter. Then we put all the data into the formula, so we get the answer is 1.8 times 10 power of negative 4 meters. That's all from us. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syamil bin Muhammad Ismail and my teammate is Muhammad Azriman bin Aznan. Today we're going to present question number 4. 4A. A laser beam of wavelength 632.8 nanometer is incident on a double slit 0.2 mm apart. Determine the distance between two consecutive bright fringes on a screen 5 meter away from the slit. From the question, the value that we can obtain is the value of wavelength, the value of distance between slits and screen, the value of separation between double slit. So, the value of wavelength is 632.8 nanometer. The value of separation between double slit is 0.2 millimeter, and the distance between slit and the screen is 5 meter. So, the question wants us to find the distance between two consecutive bright fringes, and we're going to use the formula delta y equal to lambda d capital D over d. So we just have to insert the value of delta of lambda, d, capital D and small letter d, and the answer is 1.582 to the power of negative 2 meter. 4B will be continued by my friend.
For question 4b, in a Young's double slit interference apparatus, by what factor is the distance between adjacent light and dark fringes changed when the wavelength of the source is double? So the answer is, when wavelength increases, then the distance between adjacent light and dark fringes also increases by factor 2. That's all from us. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. We are from group 5. I am Nurul Aunia Afifah binti Ahmad Zahidi.
I am Nadia Farhana binti Muhammad Zamri.
I am Nurul Akila binti Abdul Salam. Today, we will present to you question number 5.
Question 5a. A light source emits visible light of two wavelengths. Each of wavelength is 413 nanometer, which is lambda 1, and 510 nanometer, which is lambda 2. If the separation distance between the two narrow slits is 0.025 millimeter, which is small d, and screen is at a distance of 1.5 meter, which is capital D, from the two slits, calculate the separation distance between the third order bright fringe, which is M.
For the solution, first I want to explain to you about the arrow. For the long black arrow is y2 equal to lambda 2, and for the small black arrow is y1 equal to lambda 1. So now we want to find the separation distance between the third order bright fringe, which is small orange arrow.
So to calculate the answer, we use the formula y1 equal to m lambda capital D over small d. So we substitute the value from the equation into the formula. But first we need to change the unit to SI unit first. So we multiply 430 with 10 to the power of negative 9 and 0.025 with 10 to the power of negative 3. So we get y1 for 0.0774 m. Next, we need to find y2. We still use the same formula with y1. So we change the unit to SI unit, 510 10 multiplied with 10 to the power of negative 9, and also 0.025 times 10 to the power of negative 3. So we get y2 equal to 0.0918 m. So to calculate the separation distance, we minus y2 with y1. So 0.0918 m minus with 0.0774 m. So we get the answer, which is 1.44 times 10 to the power of negative 2 m. For question B, a Young's double slit has a slit separation of 2.5 times 10 to the power of negative 5, which is D, on which a monochromatic light beam is directed. The consecutive bright fringe on a screen, which is 1m, which is capital D, from the double slits are separated by 2.3 times 10 to the power of negative 2, which is delta y. So what is the wavelength of this beam?
The answer for this question is delta y equal to lambda d over d, which is the equation for the separate distance between the two consecutive bright fringes. So we will substitute the value that has given from this question into the equation, and then we will find the lambda and get the answer, which is 5.75 times the power of 10 the power of negative 7 meter. Thank you for watching. Bye.
Assalamualaikum warahmatullahi wabarakatuh. For the group presentation task, we from group 6 is going to present how to answer question 6 from chapter 2. For question 6a, red light of wavelength 644 nanometer from a point of source passes through two parallel and narrow slits 1 millimeter apart. The distance between the two slits and a screen is 1 meter. Determine the distance between the central maximum and the third order minimum.
From the question, we know that the wavelength is 644 times 10 to the power of negative 9 meter. The separation between double slit, which is small d, is equal to 1.0 times 10 to the power of negative 3 meter. The distance between slit and screen, d, is equal to 1.0 meter. The question asks us to determine the distance between the central maximum and the third order minimum. As we know, the third order minimum is dark fringe, which is m is equal to 2. This is the central maximum, and this is the third dark fringe. The distance between them, we can label it as y2. We can use the formula of separation between central bright fringe with m's dark fringe. We can just substitute the value, and finally, the final answer of y2 will be 1.61 times 10 to the power of negative 3 meter.
For question 6b, light with a wavelength of 6.33 times 10 to the power of negative 7 meter is used in a double slit experiment. The screen is placed 1 meter from the slits and the first order maximum is found 65.5 millimeter from the central bright spot. What is the separation between the slits?
So, for the question number 6 here, we have to point out the information given. So the first information that have been given in this question is the lambda, which is the wavelength, equal to 6.33 times 10 to the power of negative 7 meter. In this experiment, it used double slit experiment, which is we have to use the Young double slit, which is the center will be bright. Then, we all know that the screen is placed 1 meter from the slit, which is the D for this question. Then, we have to know the first order maximum if found 65.5 millimeter, which is the bright fringe. For this question, m equal to 1. So we have to know that y1 equal to 65.5 times 10 to the power of negative 3 meter, because we have to convert the millimeter into meter. So here is the central maximum, and this is first right fringe. And now we all know that y1 is here. Then the question asks us to find the separation between the slits, which means we have to find the d for this question. So we have to use the formula here, ym equal to m lambda d per d. But make sure you know what is the meaning of d, capital letter D, and the small letter d. The capital letter D is actually the distance between the slit and the screen, and the small letter d is separation between the double slit. And now we are going to substitute the value given into the formula to find the d. Then after we calculate into this formula, we will get the d is equal to 9.66 times 10 to the power of negative 6 meter.
Thank you for your attentive listening.
Wabarakatuh. We are from group 7. So today we're gonna present to you question 7 from Tutor chapter 2. I am Saidatul Naziha binti Azman with metric number 9200996.
And I'm Mashtah Munirah binti Muhammad Fahzain, 9200982. And I'm Sharifah Nakamila binti Syed Osman. My metric number is 9200969.
So for question number 7, A. In a young double slit experiment, the distance between the screen and slit is 20 m. So this is for uppercase D. And a monochromatic light of wavelength 500 nm. 500 nm is lambda, which is a wavelength. So we're gonna convert the nm into the m. So 500 nm times 10, the power of negative 9. So is incident on the slits. If the distance between the central maximum and 10 bright fringe is 3.4 cm, so our m is 10 and our y10 is 3.4 cm. So for A, calculate the distance between the two slits.
So here, we're gonna find lowercase d. So here we use equation ym equal to m lambda uppercase d over lowercase d. So when we substitute the value, we will get 2.94 times 10 to the power of negative 4 cm.
So for equation B, explain what happened to the interference pattern if the wavelength of the light is increased.
The answer is the separation distance between two consecutive fringe will increases. The distance from consecutive wavefronts are greater. Third, the interference patterns will be greater and further apart from each other.
For Truman, what happened to the interference pattern if the experiment is done in a dense medium?
First, the wavelength is decreasing. Second, the separation distance between two consecutive fringe will decrease. Third, the distance from consecutive wavefronts are smaller. Lastly, the interference patterns will be smaller and close to each other.
So that's all from us. Thank you again. I hope you guys will understand our explanation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh.
We from Group 8 would like to present our task. First of all, we want to introduce ourselves. Here the list of our group members. Now, let's move on to the question.
For question 8a, in a Young's double slit experiment, the distance between the two slits is 0.5 mm and the distance between the screen and the slits is 1 meter. When a light of wavelength 500 nanometer is incident on the slits, what would be distance between the two second bright fringe? So based on the question given, we all know that the small letter d is 0.5 millimeter. So when we convert into meter, it becomes 0.5 times 10 to the power of negative 3. So the capital letter D, it is 1 meter. For the lambda, it's 500 nanometer. So when we change to meter, it becomes 500 times 10 to the power of negative 9. So for the m, it's 2. So we use the formula of ym equal to m times lambda times capital letter D over small letter d. So when we substitute all the information given, we can get that the distance between the two second bright fringe is 2 times 10 to the power of negative 3 meter.
Question 8b. A yellow light with a wavelength of 5.96 times 10 to the power of negative 7 meter, while the slit separation is 1.9 times 10 to the power of negative 5 meter, and distance from screen to slits is 0.6 meter. What would be the distance from the central bright to the first order bright spot? So from the question given, we know that the lambda is 5.96 times 10 to the power of negative 7 meter. The small letter d is 1.9 times 10 to the power of negative 5 meter. And the capital D is 0.6 meter. And the m is equal to 1. So, we use the formula ym equal to m lambda capital D over small letter d. And then we substitute the value given, and the final answer we will get 0.0188 meter.
That's all from us. We hope that you all clear with the explanations. Thank you everyone.
We are from group 9 gonna present the question number 9. So for the question number 9a, the question is, the red light, which is lambda equal to 700 nanometer, is sent through a double slit. The slits are 4 mm apart. The light then hits a screen which is 1 meter behind the double slit, which is capital T equal to 1 meter. So the question, how far is the first bright fringe from the second bright fringe, which is delta y?
So the formula to find the separation is the delta y equal to lambda d over d. And lambda 700 we change to the meter. The d equal to 1 we get from this, and the over the d small we find at this. So the final answer is 1.75 multiplied by 10 power of negative 4 meter.
For the question 9b, the question is a violet light fall on two slides separated by 1.9 times 10 to the power of negative 5. First order bright line appears is equal to 13.2 mm from the center bright spot on the screen, which is 0.6 meter from the slide. So the question is, what is the wavelength of the violet light?
Now, the solution for question 9b. For this question, we need to use the formula ym equal to m lambda capital D over small d, and then we substitute the value ym equal to 13.2 multiplied with 10 to the power of negative 3. Then m equal to 1. Capital D equal to 0.6. And small d is 1.9 multiplied with 10 to the power of negative 5. And then we let the lambda as the terms, and we get the answer is 4.118 multiplied with 10 to the power of negative 7 meter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zidi Hakim.
My name is Daniel Hakim.
And my name is Tuan Haris.
We are from group 10 and we are going to present you question number 10. Let's go. Okay, for question number 10A, find the distance between consecutive dark fringe from a double slit interference pattern if the wavelength of light is 500 nanometer. So from this question, we know that the question wants us to find this, which is delta y. And then this is a lambda. The distance between the slit is 1 millimeter, and the distance from the slit to the screen is 2 meter. So this is a small d, and then this is big letter d, capital letter D. So the formula is delta y equal to lambda d over t. So we just need to enter this value and then we get the answer. Delta y, lambda is 500 nanometer times with d 2 meter over 1 to the power of negative 3. So we press the calculator and then the answer is 1 to meter.
For question B, two narrow slits are illuminated by a laser with a wavelength of 570 nanometer. This is our lambda. The interference pattern on a screen located x equal to 5.30 meter. This is our capital letter D. Away shows that the fourth order bright fringe is located y equal 6.60 cm away from the center bright fringe. Calculate the distance between the two slits.
Since the fourth order bright fringe from the central bright is y4, thus we use this equation y equal to m lambda d over d and substitute the value, then we will get the value of d equal to 1.66 times 10 to the power of negative 4.
Assalamualaikum warahmatullahi wabarakatuh. We are from group 11 going to present how to answer the question. For question 11a, since young double slits interference patterns are almost uniformly spaced, the distance between dark fringe is the same as the distance between bright fringe. Find distance from central maximum to first bright fringe. Let the wavelength of light is 570 nanometer. The distance between the slits is 1 millimeter, and the distance from the slit to the screen is 1 meter. We know that YDS is interference of two in-phase sources and have central bright fringe. From the question, we can figure out some information given, which is wavelength equal to 570 nanometer, and we have to convert it into meter, and we get 570 times 10 to the power of negative 9 meter. Next, we have distance between double slits equal to 1 millimeter, or 1 times 10 to the power of negative 3 meter. The slits place 1 meter from screen, and we know its order number equal to 1.
To find the answer, we can use formula y equal to m lambda d per d. Make sure you convert all of the information into meter. And we substitute the value and we get the answer, which is 5.7 times 10 to the power of negative 4 meter.
For question B, monochromatic light passes through two narrow slits 0.32 mm apart and forms an interference pattern on a screen 3.10 meter away. If light of wavelength 570 nanometer is used, what is the distance from the center of the central maximum to the sixth order dark fringe?
Firstly, we should identify the equation that we will use to solve this question. Since the question asks what is the distance from the center of the central maximum to the sixth order dark fringe, we know that we will use y equal to m plus 1 over 2 times lambda d over d. From the question, we gather four information, which is distance between slit and screen is 3.1 meter, and the separation between double slit is 0.32 millimeter. We will convert it to meter, so it will be 0.32 times 10 to the power of negative 3 meter. And the wavelength given is 570 nanometer. We convert it to meter and it will be 570 times 10 to the power of negative 9 meter. And the last one is order number, which is 5. After that, we will substitute all the value to the equation and we will get the answer is 0.0304 meter.
Thank you.
For question 12a, suppose that in Young's experiment, slits of width 0.020 mm are separated by 0.20 mm from the screen. If the slits are illuminated by monochromatic light of wavelength 500 nanometer, how far is tangent bright fringe from the central maximum? So this is the information that we gain from the question. Width of the slits, lowercase d equal to 0.020 mm. Distance from slits to screen, uppercase d equal to 0.20 mm. Wavelength lambda equal to 500 nanometer. Order m equal to 10, and we need to find ym from central maximum or central bright fringe. We can use formula ym equal to m lambda uppercase d over with lowercase d. But we need to convert the info to the SI unit. Then we can substitute into the formula like this. Ym equal to 10 multiply with 5 times 10 to the power of 2 times 10 to the power of negative 9 multiply with 2 times 10 to the power of negative 1 times 10 to the power of negative 3 over with 2 times 10 to the power of negative 2 times 10 to the power of negative 3. And we get the ym equal to 5 times 10 to the power of negative 5 meter.
B. Monochromatic light falls on two narrow slits that are 0.019 mm apart. First order bright fringe is 21.1 mm from the central line. The screen in 0.6 meter from the slits. What is the wavelength of the light? So we can get the information from the question is width of the slits, which is 0.019 mm. Distance from the slits to screen is equal to 0.9 meter. The wavelength what we want to find, m is equal to 1 while m is equal to 21.1 millimeter. So we can use this equation. Before we substitute the value, we must convert it to meter. So after substitute, we get lambda is equal to 6.68 times 10 to the power of negative 7 meter.
Okay, so for question 13a, in a double slit experiment, the fifth maximum is 2.8 cm from the central maximum on the screen, that is 1.5 meter away from the slits. If the slits are 0.15 mm apart, what is the wavelength of the light being used? So this is the info from the question. M equal to 5, Y 5 because the M is 5, equal to 2.8 cm, capital D equal to 1.5 meter, small d 0.15 millimeter, and the lambda is the one that we need to find. So since this question is about double slit experiment, it is a young double slit and it is in phase and the center always bright. So we use this equation, ym equal to m lambda capital D over small d. So the y equal to 2.8 times 10 power of negative 2 because we want to convert the unit centimeter to meter. And m equal to 5, lambda, capital D equal to 1.5, and small d 1.5 times 10 power of negative 4 because we want to convert millimeter to meter. So this is the answer, which is lambda equal to 5.6 times 10 power of 97 meter.
Okay, so we will continue with question B. Let me read the question first. In a double slit experiment, if slit 1 times 10 to the power of negative 5 meter apart, light casts the first bright band fringe 3 times 10 to the power of negative 2 meter from the central bright spot. If the screen is 0.65 meter away, what is the wavelength? Okay, so based on the question given, here is the info that we can gain from the question, which is d small d equals to 1 times 10 to the power of negative 5 meter, d capital equals to 0.65 meter, y1 equals to 3 times 10 to the power of negative 2 meter. How did I know it is 1? Because in the question it says that the first bright band, so we know it is y1. So the lambda that we want to find. Okay, so for this question, I will use formula ym equals to m lambda d capital over d small. How did I know that we need to use this formula? So from the question itself, it says that a double slit experiment. So when we find this keyword in the question, we know that we need to use this formula. So we just substitute the value based on the formula. 3 times 10 to the power of negative 2 equals to 1 lambda 0.65 divided by 1 times 10 to the power of negative 5. So we will get the answer, which is 4.615 times 10 to the power of negative 7 meters.
Assalamualaikum warahmatullahi wabarakatuh. So today we're going to present for question 14 for chapter 2 physical optics. I am Nur Humaira binti Sofyan.
I am Nur Ain Sofia binti Muhammad.
I am Anis Farhana binti Azman.
For question 14a, based on the question given, the source in Young's experiment emits at 2 wavelengths. On the viewing screen, the fourth maximum for one wavelength is located at the same spots as the fifth maximum for the other wavelength. So what is the ratio of the two wavelengths? So based on the question given, we will use the formula of the separation between central bright fringe, which is y equal to m lambda d over d. How we should know that? This is because it is stated by the word maximum. For the first wavelength, we know that it is fourth maximum for one wavelength, so the value of m is equal to 4. And for the second one, it is fifth maximum for the other wavelength, so the value of m is equal to 5. So the value of y4 is equal to y5. This is because it is stated that it is located at the same spots. Next, we just need to substitute the value of m to the equation. So we will get 4 lambda d over d equal to 5 lambda d over small letter d. Next, we can just cancel out the value of lambda, distance between slits and screen, and separation between double slits because it is same. Finally, we will get the answer ratio, which is 4 to 5.
For question 14b, a double slit experiment is to be set up so that the two consecutive bright fringes appear 1.27 centimeters apart. So we know that the delta y is 1.27 times 10 to the power of negative 2 meter. On a screen 2.13 meters away from the two slits, we know that 2.13 meter is the capital D. The light source was wavelength 500 nanometer, so the lambda is 5 times 10 to the power of negative 7. So what should be the separation between the two slits?
To search the separation between two slits, which is the small letter d, we use the formula delta y equal to lambda d over d. We substitute the value given into the equation. The final answer for the separation between two slits is 8.39 times 10 to the power of negative 5 meter. Thank you everyone for your attention. We hope that all of you can understand our presentation very well.
Assalamualaikum warahmatullahi wabarakatuh. We are from group 15 and today we would like to discuss our question, which is question 15.
Our lecturer, Mr. Sakiatul Laila binti Muhammad Jasni, and my name is Nur Masrina binti Amir Hamzah with number metric 9200992, and my friend Nur Nasira binti Ahmad Hasran 9200999.
Okay, for question 15a, the question is, if 500 nanometer and 650 nanometer light illuminates two slits that are separated by 0.5 millimeter, how far apart the second order maxima for these two wavelengths on a screen 2.0 meter away? So the d is 2 meter, the small letter d is 0.5 millimeter, the lambda 1 is 500 nanometer, and the second lambda is 650 nanometer. The m, the order number is 2, and we want to search for y2. So we use the formula y2 equal to m lambda d over d small. So we substitute the value 2 times 500 times 10 to the power of negative 9 times 2 over 0.5 times 10 to the power of negative 3. So we got the answer 4 times 10 to the power of negative 3 meter. And for the second lambda, we substitute 2 times 650 times 10 to the power of negative 9 times 2, the d, over 0.5 times 10 to the power of negative 3, and we got the answer 5.2 times 10 to the power of negative 3. So we want to search for the distance between two wavelengths. What we have to do is we have to subtract the two value that we got, 5.2 times 10 to the power of negative 3 minus 4 times 10 to the power of negative 3, and we got the answer 1.2 times 10 to the power of negative 3 meter.
For question 15b, suppose that the highest order of bright fringe that can be observed is the 8 in a double slit experiment where 550 nanometer wavelength light is used. What is the separation between the slits? Let the double slit situated 1 meter from the screen and the distance of 8 bright fringe from the center line is 0.016 meter. So for the m here is 8 because we can see this observe is the 8 in a double slit. So the lambda here 550 times 10 power of negative 9. So the capital D is 1 meter. and the y equal to 0.016 meter. So what we want to search here is the small d. So we use the formula ym equal to m lambda d over small d. The ym given here is 0.016 meter and the m is 8. The lambda is 515 times with 10 power of negative 9 and the d is 1 over the d, the value that we want to search. So we get the answer d equal to 2.75 times 10 the power of negative 4 meter. That's all from us. Thank you.
For question 16a, red light of wavelength of 700 nanometer falls on a double slit separated by 4 mm. If the distance of the first order bright fringe from center line is 5 times 10 to the power of negative 4 meter, what is the distance between the screen and slits? So from this question, we have found some information which are lambda equals to 700 nanometer and we will convert it to meter unit and it will be 700 times 10 to the power of negative 9 meter. Next, we will find smaller d equals to 4 millimeter and we will convert it to meter unit and it will be 4 times 10 to the power of negative 3 meter. And then we will find m equals to 1 because it is the first order bright fringe. And then we will find y1 equals to 5 times 10 to the power of negative 4 meter. So what we need to find is the capital D. After we have found these informations, we need to substitute it into the formula ym equals to m lambda capital D over smaller d. And then we will calculate it and we will get the final answer, which is capital D equals to 2.86 meter. That's all from me. Thank you.
Question 16 Part B. The interference pattern of a Hainan laser light in the bracket given lambda equal to 632.9 nanometer. Passing through two slits 0.031 mm apart. Is projected on a screen 1.0 meter away. Determine the distance between the adjacent consecutive bright fringes. First, let us track the information given in the questions. The information given is lambda equal to 6.392 multiply 10 to the power of 2 multiply 10 to the power of negative 9 meter. The next information is the distance between two slits, which is small letter d. The value is 3.1 multiply 10 to the power of negative 2 multiply 10 to the power of negative 3 meter. The last information given is the distance of a screen from slits. The value is 1.0 meter. The question asks us to find delta y, which is the distance between adjacent consecutive bright fringes. We can find delta y using this formula. Delta y equal to lambda multiply capital letter D divided small letter d. Before we substitute the value in the formula, we should convert the value into SI unit. After substitute the value, the final answer is 2.04 multiply 10 to the power of negative 2 meter.
Question 17. In a Young's double slit experiment, it always produces in phase coherent source. The separation distance y between the second order bright fringe and the central bright fringe on a flat screen is 0.0159 meter. This is y. When the light has a wavelength of 425 nanometer, this is lambda 1. Assume that the angles are small enough so that sin is approximately equal to tan. Using the same setting of experiment, find the separation y. This is what we want to find. And this is yb. When the light is changed to a wavelength of 552 nanometer, this is lambda 2. First, we must sketch like this. This is central bright fringe and this is second order bright. So distance between these two is YA 0.0159 meter. So for separation YB is we must use this formula y equal to m lambda d over d. You can refer page 35 course book to use this formula. So for the first wavelength, we can use this formula YA equal to m lambda 1 d over d, and for the second wavelength, we can use the formula YB equal to md over d multiplied by lambda 2. Since the combination md over d never change, we can solve for YB by dividing the equation YB dividing by YA. So we simplify this equation and md over d is same both sides, so we can ignore both of them and we can solve for YB is YB equal to YA multiplied by lambda 2 over lambda 1. Then we just substitute the value of the equation like this, and both of lambda is in nanometer, so we must multiply by 10 to the power of negative 9 to convert nanometer to meter. Then we just use the calculator and we will get the answer 0.02065 meter, or we can change the answer to the prefix like this final answer 2.065 multiplied by 10 to the power of negative 2 meter. The